Good day, ladies and gentlemen. You're all very welcome to this Saturday's technical session of the CNPS. Now, today we're reverting to a very fundamental topic that has exercised our imagination, to wit, special theory of relativity. And we're delighted to have Joe Sorge actually here today, who has done some work on this. He's produced some very interesting videos on the subject and some very interesting analysis of the basics of the Lorentz transformation and so on. What we're entitling today's talk is basically Einstein's clock synchronization method requires that two clocks in the same inertial reference frame report different time readings, which would seem on the face of it to be absurd. So I'll just have a look at what we agreed with Joe as the description. Joe is saying that Einstein's clock synchronization method requires that two clocks in the same inertial reference frame report different time readings based on A, their speed relative to an observer frame, and B, the distance separating the clocks, which is basically clock difference is minus V dx dash over c squared, where V is the relative speed and c is the speed of light and x is the separation distance. Yeah, he's got it here. And dx dash is the proper distance separating the clocks in the clock frame. Since special relativity allows the choice of observer frame to be arbitrary, all frames are equal, conventional SR doctrine required different clock readings for different observers. This is obviously unworkable and points to the obvious solution that speed V must be measured relative to a universal preferred frame, reference frame. And it's hosted by me, Ian Cowan, as usual. Right. So as usual, we have a number of people coming in now. I can see them on the Facebook and YouTube social media, and they'll be discussing among themselves all that, and we'll be keeping an eye on that. That's fine. But if they have any specific questions for Joe, they might just say question for Joe so we don't miss it. And we'll take their questions first and we'll discuss them. And we have a number of people in the green room. I see they're still coming in. And afterwards, we'll bring people up. If they want to engage in a more detailed discussion with Joe, we'll allow that. So Joe has a video, I think, which he's going to commence showing, and he will be introducing us to it. So Joe, I'm going to give you the floor, and you might like to say a brief word about yourself, because we sort of exchanged experiences, and I cut you off a bit because we were coming to the start time, but I'd like you to say that to the people participating rather than just me. So I'm going to hand the floor over to you. I will be in the background. If there's any problem, just shout, and if you say please show the video, I just have to press a button and the video will be up.
Yeah.
Okay. So the floor is yours, Joe.
Well, thank you, Ian. Appreciate it very much. And I'm honored to be here. Ian asked me to give a little bit of personal background before I got going. I actually went to medical school after graduating MIT in chemistry and physics, chemistry and biology. And because my mom wanted a doctor in the family, and I didn't know what I wanted to do in life. So I went to medical school and quickly realized it really wasn't interesting to me. But I did finish it. I didn't want anybody to say I wasn't smart enough to finish it. I couldn't live with that. So I finished medical school. But right after medical school, I decided to do a postdoctoral fellowship in molecular biology. So I studied with Jim Watson of Watson and Crick at the Cold Spring Harbor Laboratories, where I learned molecular biology for a couple of years. And then I got a job as an assistant professor out in La Jolla, California, in a molecular biology oriented medical laboratory, and cloned the gene for Gaucher disease, which we eventually used to repair the enzymatic defect in cell culture, but never tried it in humans. This was 1983, and the world wasn't ready for that yet. So I got a little bored, and I wanted to get back to molecular biology, and I started a company, a biotech company out in California, in molecular biology, and just thought it was going to be something to make a little money on the side so I could go out to dinner and maybe buy a nice car. But it did very well. And the company grew to 500 people. And after a while, I found myself doing HR issues and insurance policies and talking to investors rather than doing bench science. And again, I didn't like it. So I decided to sell the company and thought maybe I'd go into retirement. But that didn't work out so well. I just can't sit on a beach anywhere. So I wanted to do something to keep my mind occupied, but at the same time make a little income. And I started a real estate business out in Las Vegas, believe it or not, and did that for about, well, I'm still doing that. So part of my time is involved in running this real estate company. We now have hundreds of apartments and an office building. But what I really love is what I'm doing here. And because it's intellectually interesting, and I'm just delighted to be here and able to share this with you. So I'll get into the science. If there are any questions, how will I know? Will it be in this private chat on the side of my screen?
Well, there are two chats there. There's the private chat and the general comments. Sir, I think you should be able to see both.
Yes, I can.
Okay. But I wouldn't worry too much about that, because the important thing is that we devote our attention to what you're saying. We can deal with these after. I'm going to keep an eye on the comments. And I have actually said in the past that if there's anything really urgent that don't understand what he said, how did he pronounce that word?
Yes.
You probably won't mind interrupting. But in general, we ask people to wait until the end of the lecture, and I'll bring up these questions and answers and similar comments. So you don't need to worry about that, Joe. Leave that in my hands.
Okay. So, all right. So let's jump into the topic. So I had a friend who asked me to explain special relativity to him because he knew I was science oriented, and I frankly couldn't do it. I started to read about it. I don't have a physics background, but I started to read, and it didn't make sense to me. I just felt like there was something wrong with it. And I told him, I said, I just can't put this together. There's just too many odd assumptions, and I just don't feel that it's right. And in particular, this is one assumption of length contraction, which with my chemistry background, I just couldn't figure out how these molecules would be allowed to squish together without there being some kind of vast amount of energy used to contract these substances. So I said, there's something wrong with this. Give me another week and I'll try to figure it out. And that was 5 years ago. So I have been, toying with it in my spare time, and really, started this video series, and which has been very interesting because, most of the comments are, oh, why don't you take a physics course and learn physics the right way? You don't know what you're talking about. A lot of the comments are really insulting, and they assume that I don't understand special relativity at all. I think I've learned enough of it now that I really understand the subtleties of it. And then occasionally I'll get a comment from someone that says, oh, thank you so much. I've had my doubts about special relativity all over these years, and what you're saying makes a lot of sense. So at least I get a few of those once in a while. So the question is, can an experiment be devised to really test special relativity in a way that it has not been tested to date? Always people say, what are you talking about? Einstein has been proven correct in so many ways and so many experiments. How could you possibly think there's something wrong with it? And the truth is that experiments have been done. Many experiments have been done, and certain things have been validated. But other aspects of special relativity have not been validated, and particularly length contraction. No one has ever really demonstrated that occurs. I know there is some phenomenon in electromagnetism where the field condenses in one dimension but not in the other, but I think that's more of a Doppler associated effect and not length contraction. And that'll be a topic for a future video. But one of the things that I noticed fairly early on is that Einstein had a very interesting way of synchronizing clocks. And if you look at his 1905 relativity paper, it's based on, in section 1 of the paper, he basically said everything is based on this way of synchronizing clocks. And when he synchronizes clocks, he sends light from one clock to a mirror where there's a second clock, and then the light is reflected back to the first clock, and he measures the round trip travel time, and then he divides that in half arbitrarily, and he says that we will deem that half time to be how long it took to get to the mirror, and therefore we will adjust this mirror clock so that the reading on the mirror clock, when the light signal hits the mirror, the time reading on the mirror clock will be 1/2 of the round trip time elapsed from the start to the end. And so, and almost, it's surprising, I'd say 95% of physicists just don't know that this is what he did. And there are a series of articles back starting in the 1920s and going from there about what's called the Einstein clock synchronization convention. And there were some scientists that challenged it at the time. And for some reason, they are called the conventionalists. They say, oh, this was just a convention that Einstein chose, and you don't have to make the travel times 1/2 each way. It could be 2/3 one way, 1/3 of the time and the other way. It could be arbitrary. No one really knows. And then there are the anti-conventionalists who say, no, the conventionalists don't know what they're talking about. Einstein's way of doing this is the only practical way of synchronizing these clocks. And there's actually a great Veritasium video on YouTube now called "No One Has Ever Measured the One-Way Speed of Light." And I think that's fairly accurate. It is almost impossible to measure the one-way speed of light because you either have to synchronize the clocks on either end of this distance over which light speed is measured, which presents you the challenge of, well, what do you use to synchronize the clocks? If you use a light signal, you're going to get this odd delay effect, and you're going to have to figure out how to adjust that downstream clock in some way. Or you need to come up with some type of a time of flight measurement, but that requires putting typically wires at either end and taking those wires back to a oscilloscope or some other measuring tool, and you get delays through the electric field that's going back to your measuring tool. And so there's a light delay, and then there's electromagnetic field where the electric current is reported back to the measuring tool, and so you get a counterbalancing of the delays. So really, no one has truly measured the one-way speed of light, and I can talk about this for hours some other time. But what I wanted to do is come up with a way to determine whether we could do an experiment without having to adjust a clock. Can we just use another way of measuring elapsed time other than the separation of two clocks and the difference between their readings? And so I did, and that's what this video will be about. And, you know, Ian nicely introduced the topic, and he said that, you know, according to Einstein's paper, these clocks will be reporting different readings based on a formula. And the formula takes 3 factors into account. One of them is the speed of the clock frame moving relative to an observer. So Einstein always said that everything is relative. You can choose whichever observer you want to choose, and you can choose whatever moving frame you want to choose. And everything there will be relative. This observer, you could have 20 different observers, and they each have their own relationship to the moving frame, but that everything in special relativity will work out. But the problem is that the synchronization of clocks is dependent on the speed of the frame relative to the observer. And so if you have a second observer who's moving relative to the first observer, then their relative speed to the clock frame will be different than the relative speed of the first observer to the clock frame. And since the actual readings on the clocks, the adjustment one should make to the mirror clock, the downstream clock, is dependent on the speed of this frame relative to the observers, then it demands that you make different adjustments on the downstream clock depending upon which observer is looking at that clock. And I just think that's not possible unless you believe in multiple universes and a multiverse, and there, each clock is in a different universe, which again, I have more trouble understanding that than special relativity. And so I think there's inconsistencies in special relativity. The problem with trying to prove that the downstream clock is actually reading a different time is that for the same reasons that you can't measure the one-way speed of light, it's also almost impossible to measure the reading on that downstream clock without dealing with this same delay issue of the transmission of signals from the upstream clock to the downstream clock and back. So I came up with a thought experiment that would allow us to sort this all out without the need, excuse me, to have that second downstream clock. And so, and I came up with a thought experiment, and what the experiment shows is that we don't live in a universe that's all relative, that there must be some, and people call it a preferred frame of reference, a universal frame of reference. I think of it as something that mediates electromagnetic signals through the vacuum of space. I don't think it's the same as Lorentz's ether. I think it's a little bit different, and we won't get into why I think it's different today, but it's similar. I think there's probably a field that mediates electromagnetic signals, and that field is, let's call it static in the universe, something like a Higgs field, but a field for the electromagnetic forces. And that, light signals pass through a universal stationary field. So, and I will now start my video to demonstrate why I think that's true. And I just want to say, I've been seeing many comments come in. I probably should get my glasses on so I can read them. Give me 1 second here. But if at any time, Ian, you see that there's a significant question, like they can't understand what I'm saying, or that something needs to be clarified, or someone's challenging what I'm saying, please let me know, and we can stop the video and tackle that.
Yeah, I'll certainly do that. By the way, just a small housekeeping. You don't have any slides that you may wish to project at some time, do you, Joe?
It's all the video, and I'll just pause the video on occasion to give us a little bit of time to digest the material. Fine. But no, it's all going to be the video. So if that works, I will start the video. I'm going to skip the first couple of minutes where I just say a couple of foolish things. And I've already given you some introduction, so we'll jump into the meat of the video. And I'm going to try to stop it occasionally to elaborate where I think some of the points are critical. So, what is meant by the principle of relativity? The principle of relativity was first attributed to... Were you all able to hear that sound, the audio?
Well, I can certainly hear it, and I'll just check with one other person. I'm sure it's fine.
All right.
For example, Jim, I assume that was all right. You've got your finger up.
Yes, I can hear well. Thank you.
Perfectly.
Excellent.
Thank you.
Okay.
Perfect.
All right. We will jump in until the first pause. Here we go. Galileo Galilei, who in 1632, in his dialogue concerning the two chief world systems, used an example of a ship floating on a smooth sea at constant velocity. He stated that an observer below deck would not be able to discern if the ship was moving. In other words, that the laws that govern the motion of objects would operate the same regardless of the speed of the ship. The principle was later broadened to the equations describing the laws of physics must have the same form in all inertial frames of reference. This implies that there's a symmetry to the laws of physics. A law of physics must look the same to one inertial observer as it does to another inertial observer. Einstein and Lorentz took this further. They believed that one could use certain equations or transforms to predict certain quantities within an inertial system by knowing similar quantities in another inertial system moving at a known speed with respect to the first system. Einstein stated in his 1907 paper on special relativity,
if one solves the transformation equations with respect to x, y, z, t, one obtains the same equations, except that the primed quantities are replaced by the corresponding unprimed quantities, and conversely, and v is replaced by minus v. This also follows directly from the principle of relativity.
Einstein was saying that the transformation equations, which we often call the Lorentz transforms, are symmetric, such that if an observer in the first inertial system believes that a second inertial system is moving at speed v, then an observer in the second inertial system will observe the first inertial system to be moving in the opposite direction at speed negative v, and that either observer can describe the motion of the other observer using a set of symmetrical equations. But Einstein added an interesting paragraph to his 1905 relativity paper.
If at the points A and B of K, there are stationary clocks which, viewed in the stationary system, are synchronous, and if the clock at A is moved with the velocity v along the line AB to B, then on its arrival at B, the two clocks no longer synchronize. But the clock moved from A to B lags behind the other, which has remained at B by 1/2 TV squared over C squared.
I've unpacked this statement in some of my other videos, but now let's see what it means to the principle of relativity. Einstein tells us that if system K clocks are initially synchronized according to the method described in the first section of his 1905 paper, then a clock that moves with respect to that system will beat slower than a clock that remains stationary. That's why the reading on clock A will lag behind the reading on clock B when the clocks unite. This effect is not some illusion related to the relativity of simultaneity. Einstein described a predictable and measurable difference in the readings of clocks A and B when they come together, a concept that has been supported with experimental evidence. I'm going to show that system K does not need to be stationary in some absolute sense in order for his approximate formula to be true, provided that the clocks of system K were initially synchronized pursuant to Einstein's protocol. I'm then going to describe an alternative experimental setup using the principles of the 1905 paper, where the final difference in the readings on the clocks will depend on the speed throughout space of the system containing the clocks. In other words, observers in the system of clocks will observe different outcomes depending on how fast their system travels with respect to some universal reference system. This novel experiment will demonstrate that the principle of relativity is a fallacy, and that special relativity unknowingly proves that clock tempo and light speed are influenced by some universal preferred system. If I succeed, it'll be huge. So, to illustrate the concepts, I'm going to generalize Einstein's setup. Let's say that there's a system, S prime, that can be observed from system K. Let's say that clock B prime is stationary at the origin of system S prime, and that clock A prime moves over to clock B prime. If we wish to quantify the difference in the readings displayed on clocks A prime and B prime when they unite, we can do so with the following formula. We're an observer. So I'm going to stop here for a second because this is a big, hairy formula that I just threw on the screen. And I just want to tell you that the concept here is I'm throwing out a formula, and then I'm going to break the formula apart piece by piece. And then I'm going to demonstrate that if you put in the assumptions that Einstein made in his 1905 paper, this formula agrees with the result that Einstein published in the formula in the paper. And just so that you see what I'm doing here, dtk, and by the way, I use the little d. People say, well, that's calculus, that's an infinitesimal. I just don't like typing the Greek delta all the time. I'm not, on my keyboard, I have to hit too many keys, so I just use D instead of delta. But it just means the difference in time. So it's the difference in time on this clock up here in system K from the moment that the clock A prime was at its origin, not its origin, but at this point, and moves over to being adjacent to clock B prime. So that's elapsed time, but it's elapsed time from the point of view of an observer in system K. And remember that Einstein believed that these clocks in system S prime will beat at the same tempo as the clocks in system K if system S prime is stationary relative to system K. But if system S prime is moving relative to system K, then Einstein proposed that these clocks will beat at a slower tempo by the Lorentz factor. And you would actually take the time elapsed on the system K clock and divide by Lorentz's gamma factor, which if you flip it upside down and multiply times the root inside the factor, it would be the square root of 1 minus the speed of clock A prime over c squared. And he would say clock A prime beats slower than clock K by that factor. And then clock B prime, which is stationary within system S prime, but may be moving relative to system K a little more slowly through space than clock A prime. Its time dilation or slowing of system B prime clock would be the square root of 1 minus the speed of clock B relative to clock K squared over c squared. And then Einstein threw in a factor, which I call the clock offset factor. I've seen it referred to as the spatial gradient of clock readings. This is what I talked about in the introduction, where if you use a light signal to synchronize clocks A prime and B prime at the very beginning, if system S prime is stationary, then the speed of system S prime V sub S prime will be 0, and this factor goes away. And what that means is that clock A prime and B prime will report identical readings if the system S prime is stationary relative to system K. But if system S prime is moving relative to system K, then this is the speed at which it's moving. And then dx prime is the distance that separates clocks A prime from B prime, and then over c squared. And this you can find in the Lorentz transformations. You just need to take the Lorentz transform for time in the stationary frame and rearrange it and solve for time in the moving frame. And this will pop out in that equation as the adjustment that Einstein makes to the downstream clock. It's a minus, and what you do is you set the downstream clock to a slightly earlier time than the upstream clock in order to force the speed of light to be the same in both directions. Not truly the same in both directions, but the readings on the clock will deceive you into believing that the speed of light is the same in both directions. So I didn't make this up. This is in the Lorentz transforms. Very few people are aware of this. It's cryptically written in the 1905 manuscript, but it's there. Einstein in section 1 talks about the way to synchronize clocks. And if you rearrange the Lorentz transform, you get the actual, you can quantify the amount by which the clocks are off, the offset. So the overall formula here for the difference between the readings on clock A prime versus B prime at the end of this movement will be the elapsed time on the system K clock times the square root, the first Lorentz factor, inverse of the first Lorentz factor for clock A, minus the inverse of the Lorentz factor for clock B, and then also for this clock adjustment that taking into account that clocks A prime and B prime were not reporting the same reading at the beginning of the movement. So now what I'm going to do, I'm going to start the video again and show that if system S prime is stationary, which is what Einstein said in his 1905 paper, he said if we take two clocks in a stationary system and move one clock over to the other clock, we're going to get a difference in time readings of 1/2 t, and t being the reading up here from the observer, times v squared over c squared, where v squared is the speed of clock A prime relative to clock B prime. So unless there are any urgent questions, I will begin the video again. And system K measures the speed of system S prime, labeled V sub S prime, relative to system K. And the time dt sub K is the system K time for clock A prime to travel to clock B prime. Only one system K clock is needed to measure the speed of clock A prime. Let's call it clock K. Note that elapsed time dt sub K is expressed in the time units of clock K. In other words, governed by the tempo of system K clocks. Observers in system S prime can measure the initial proper distance separating the clocks, we'll call it dx prime, using system S prime measuring tools. Since clock B prime is stationary in system S prime, clock B prime and system S prime both travel at the same speed, V sub S prime, with respect to system K. And clock A prime travels at speed V sub A prime with respect to system K. This formula accounts for the difference in tempo of clocks A prime and B prime with respect to clock K, and the rightmost term accounts for the fact that Einstein deemed the clocks to be synchronous within the system of clocks. I've included the Greek symbol delta in the subscript to dt prime to reflect initial Einstein clock synchronization. We covered Einstein clock synchronization extensively in episode 7.2. In short, this procedure creates a difference in readings between clocks A prime and B prime as observable from system K. When system S prime is moving with respect to system K, the clock offset term is equal to the speed of system S prime with respect to system K times dx prime over c squared. But when the speed of system S prime is 0, the V sub S prime term will be 0, and clocks A prime and B prime will report the same reading once synchronized, even though the two clocks are initially separated by distance dx prime. In other episodes, I've referred to the difference in clock readings as a clock offset, or as a spatial gradient of clock readings. Since our clock B prime is stationary in system S prime, we can simplify our formula by replacing V sub B prime with the speed of system S prime. We can then write speed V sub A prime as V sub S prime plus the incremental speed at which clock A prime approaches clock B prime as measured from system K and system K dimensional units. We will call that incremental speed dV sub A prime. When the speed of system S prime is 0 relative to system K, we can simplify our general formula to match Einstein's example. And if we use a Taylor series expansion a second order to approximate the square root term, we get approximately 1/2 the time elapsed on clock K times the incremental speed of clock A prime squared over c squared, when the speed of clock A prime is very slow compared to speed c. In Einstein's example, he labeled the incremental speed of the moving clock, what we call dV sub A prime, simply v. And so he obtained a difference in final clock readings of 1/2 dt times v squared over c squared when ignoring Taylor series expansion terms of fourth order and higher. So I came up with the same answer Einstein published in his 1905 paper. That doesn't mean that my formula is necessarily correct, but at least it means that my formula is consistent with his thinking. And again, I didn't make any assumptions that are outside of the scope of special relativity. It's simply that clock A prime is going to be time dilated by the Lorentz factor based on its speed relative to clock K. Clock B prime is going to be time dilated based on the Lorentz factor relative to its speed relative to clock K. And then the clock offset term here in Einstein's 1905 paper, he said that what I'm calling frame S prime was stationary, meaning that it had 0 speed relative to clock K. So the clock offset term goes away. And when you do that, you get Einstein's formula for the difference in the readings between the two clocks at the moment that clock A prime moves over to clock B prime. Okay, So I'm assuming since Ian hasn't interrupted me, everything's okay so far. And I'm going to continue the video. Oh, but I'll just say that now what I'm going to ask is, do we get the same result if frame S prime is moving? Because if the theory of relativity is correct, then we should get the observers that are in frame S prime, that the difference between clocks A prime and B prime and S prime, this final outcome should be independent of the speed of frame S prime relative to system K. That's the whole principle of relativity, that there's no absolute frame. And so therefore, if we run this experiment using a moving system S prime, we should get this same formula at the end. And so now I'm going to go through a kind of a laborious test of that.
Beautiful. We completely agree with Einstein for once. Interestingly, this concept actually sparked discussions in 1911 that led to the twin paradox, which we cover in episode 10. So if Einstein was correct, then the difference in the readings of clocks A prime versus B prime should be an observable and quantifiable end state when they unite. Good. We have a testable experiment. And if the principle of relativity is true, then the difference in final clock readings should be the same, regardless of whether we perform the experiment in system capital K or system small k or system S prime, etc. Because according to special relativity and the Lorentz transforms, we should always be able to swap a stationary system for a moving system and vice versa.
You know, I happened to see one of the comments, and it was a question: does the presenter agree or disagree with the concepts of time dilation? You know, there have been experiments showing that atomic clocks slow down in GPS satellites. I don't know if the Hefefi-Keating experiment was done well enough to believe in it, but you know, there are many experiments showing that the frequency of light emitted from moving emitters changes depending on the speed of the emitter. And so I wouldn't be surprised if there's some fundamental change in the frequencies inside of atoms for whatever's going on in there as they move through this universal preferred frame. And so I would say, yeah, I lean in the direction of believing that time dilation is real. I don't believe in length contraction, but I'm not surprised if the speed of atomic clocks, I don't know about spring-based clocks or pendulums, that's a whole nother can of worms. But you know, I think atoms, the frequency inside of atoms probably is changing relative to this universal preferred frame, depending upon how fast that atom is moving through space. So, but it doesn't matter what I believe. Everything in this video uses Einstein's assumptions. Okay, I'm running this thought experiment with all of his postulates and assumptions. I'm not including anything from me in here. I'm just using his weapons against him, let's say.
So for any given speed at which clock A prime travels through system S prime toward clock B prime, we should always find clocks A prime and B prime to report the same measurable difference in the readings when they unite, whether system S prime is considered moving or stationary. According to special relativity, the laws of physics should be the same regardless of the inertial system. So let's take our formula for the difference in clock readings and make some substitutions so that we can determine if the difference in readings on clocks A prime and B prime remains constant regardless of the speed of system S prime relative to system K. First, we note that the Lorentz time transform for elapsed time on clock B prime can be written as dt sub k measured on a system K clock times the square root of 1 minus v sub S prime squared over c squared minus the clock offset term. The difference in readings on clocks A prime versus B prime can then be written as dt prime sub B prime as adjusted for clock offset minus dt measured on clock K times the square root of 1 minus the speed of clock A prime with respect to system K squared over c squared. And then because, and only because, clocks A prime and B prime were Einstein synchronized at the outset, we can use the following identity, which can be derived from the invariant interval in addition to the inverse of Einstein's velocity addition formula to arrive at the k squared over c squared. And then because, and only because, clocks A prime and B prime were Einstein synchronized at the outset, we can use the following identity, which can be derived from the invariant interval in addition to the... Okay, so I know I threw a lot up on the screen all at once. I don't think we have time today to check my algebra. I've checked it 50 times. And it works. And you're going to see we're going to get the result that Einstein predicted at the end. So I think I did the algebra right here. But if any of you want to proof my work, we'll be publishing this on our Ask Us Whatever website where these videos are posted. They're also on YouTube. And you can see that these relationships are valid. The inverse of Einstein's velocity addition formula to arrive at the following intermediary formula for dt prime sub b prime delta. Please note that Einstein's velocity addition formula and its derivatives require the use of clocks that have been offset using Einstein's unusual synchronization protocol. Use of this formula is not appropriate for setups in which there is only one clock present, such as in a Sagnac experiment or when clocks have been absolutely synchronized. Now we can spot a formula for dt sub k, the term in the blue box, in this intermediate formula. The following is merely a variation of a formula that Einstein published in his 1905 relativity paper. The time elapsed on clock k is equal to the length contracted distance traveled by clock a prime, dx prime, divided by gamma sub v sub s prime, divided by the amount by which the speed of clock a prime exceeds the speed of frame s prime. And you notice I say the length contracted distance between clocks A prime and B prime. Again, I don't believe in length contraction, but I'm using Einstein, everything Einstein here. So you have to contract the distance between the clocks when you're looking at them from system K. You have to assume that the distance between the clocks has been contracted by the Lorentz gamma factor. And again, I'm not making any of this up. This is all coming from special relativity. Prime. We can then rearrange our formula for dt prime sub b prime delta to arrive at the conclusion that the time that elapses on clock b prime times the inverse of the Lorentz factor evaluated at the speed of clock a prime with respect to system s prime is equal to the time that elapses on clock k times the inverse of the Lorentz factor evaluated at the speed of clock a prime with respect to system k. The formula for the difference in clock readings can then be rewritten as dt prime sub b prime delta times 1 minus the square root of 1 minus v prime sub a prime squared over c squared. We can then approximate this to second order with a Taylor series expansion and arrive at Einstein's formula, written with respect to both systems s prime variables and system k variables. In other words, Einstein's formula works whether we measure time and speed in system S prime or system K, regardless of the speed of either system with respect to the other. And since dt prime for clock B prime is equal to dx prime over v prime sub a prime, we see that the difference in clock readings will remain constant, provided that we choose a fixed v prime sub a prime, irrespective of the speed of system S prime. And also, and this is extremely important, provided that v prime sub a prime was measured in system S prime using distant clocks that had been Einstein synchronized at the outset. Again, we find that the principle of relativity holds true under these conditions. The difference in clock readings is independent of the speed of system S prime, provided that clock A prime speed is a fixed quantity within system S prime, and that Einstein synchronized clocks are used to measure times and to compute speeds in system S prime. So, excuse me if I'm belaboring things too much. I don't know the backgrounds of people who are watching, but really what happens is you get the same result. You get the same end result as long as the speed of clock A prime within system S prime is the same. The speed of system S prime doesn't matter.
if you use Einstein's equations and you synchronize the clocks ahead of time the way he said you should synchronize, you get the same result. And this is a physical and observable result. You could look at these two clocks at the end of this experiment and read the difference between the two clocks. And if you believe in special relativity and the time dilation, then you should get the difference between the clock readings should be identical, no matter how fast frame S prime is moving through space. So again, so far in this video, I'm supporting everything that Einstein says about relativity. I'm using all of his equations, and running through it and saying, yes, the formulas and everything are consistent with special relativity. If you do the experiment his way, in which you have to start out with two distant clocks that are not reading the same time. And as long as you adjust them his way, then the end result will always come out the same. So then I said, well, could I come up with an experiment where you don't use two distant clocks? Is there any other way we could do this experiment? And that's what I'm going to play for you now. And again, what you're going to see, again, follows all of his assumptions. There's nothing novel that I'm introducing here. I'm just using time dilation the way that Einstein defined it.
So once again, Einstein succeeds. He conjured up a method that appears to preserve the principle of relativity, provided we follow his rules regarding the use and synchronization of distant clocks. But what if we could design an experiment that makes the offset of clocks irrelevant? Would the principle of relativity still hold true? Clock offset is only required by special relativity theory when we measure one-way trips in the moving system along the axis of motion, what we call the x prime axis in system S prime. But what if we make round-trip measurements instead? In which case the downstream and upstream clock offsets cancel each other exactly. The answer, I promise you, is going to be fascinating. But first, we must dispense with an objection typically raised in the story of the twin paradox, where a moving clock partaking in a round-trip journey must change direction at some point to return to its origin. If we can avoid the changing of direction or otherwise accelerating or decelerating our clocks, we can avoid these objections. Let's use a little creativity with clocks A prime and B prime. Let's say that clock B prime is stationary at the origin of system S prime as before. But now let's consider a clock A prime as moving along the x prime axis parallel to the direction of system S prime motion. When clock A prime reaches clock B prime at the S prime origin, clocks A prime and B prime are synchronized. Note that if we use Einstein's synchronization method under conditions where the distance between these clocks is 0, both clocks will report the same clock reading, regardless of the speed of system S prime relative to system K. We can even reflect this in our master formula for determining the difference in clock readings. So whether we use Einstein's synchronization method or the simple matching of clock readings at the origin, we've synchronized clocks A prime and B prime to report exactly the same time reading at the instant they are side by side. Next, we'd like to measure the speed of clock A prime in system S prime without resorting to the use of distant clocks that have been offset with Einstein's clock synchronization method. Why? Well, it's not widely appreciated, but the use of such offset clocks will bias the computation of travel speeds. The use of distant offset clocks to measure elapsed time can deceive observers in system S prime into believing that identical downstream and upstream speeds are not identical, or that non-identical downstream and upstream speeds are identical, which is the trick that Einstein used to convince observers in moving systems that light travels at a constant speed c in either direction. And unless one intends to manipulate time measurements to satisfy some preconceived postulates, there's no need to use distant offset clocks to measure speeds and times when local measurements will suffice. Observers in Einstein's stationary system K do not require distant offset clocks to determine the speed v of another system. They can simply measure the speed of another system passing a single clock that is stationary in system K. We can choose to do the same in system S prime, such that a single clock in S prime is used to measure elapsed times in order to compute frame S prime speeds. If clock A prime were aboard, let's say, a spaceship of known proper length in system S prime, we can divide its proper length by the amount of time that elapses on clock B prime from the instant the front of the ship passes clock B prime to the instant the rear of the ship passes clock B prime. So how do we measure round-trip durations without accelerating or decelerating any of the clocks? Let's add another clock, C prime. Clock C prime happens to be traveling within system S prime at the same speed as clock A prime, but in the opposite direction. As with clocks A prime and B prime, clock C prime speed is measured using a single clock in system S prime and a single clock in system K. When clocks A prime and C prime cross paths, observers in system S prime can measure the proper distance dx prime sub 1 from that location to the S prime origin using system S prime measuring tools. Furthermore, when clocks A prime and C prime cross paths, clock A prime sends a timestamp signal to clock C prime. In other words, information is transferred from clock A prime to clock C prime, communicating the reading on clock A prime at that instant. Clock C prime records its own time reading at that instant, and in order to make our future computation slightly easier, resets its own clock reading to the exact time reported by clock A prime. Clock C prime has essentially been Einstein synchronized with clock A prime when they meet, again without producing a clock offset. No clocks change direction or speed. No offsets are introduced into any of our clocks to distort or to artificially manipulate the outcome of time or speed measurements. And as you can see in the animation, when all three clocks move in the positive X direction in system K, clocks A prime and B prime begin side by side, whereas clock C prime begins slightly downstream. Clock A prime moves faster than clock B prime, which moves faster than clock C prime. After time dt sub k1, clock A prime reaches clock C prime, and clock A prime shares its time reading with clock C prime. Clock B prime has not moved as far as clock A prime during this period, but after additional time dt sub k2, clock B prime approaches clock C prime, where they compare time readings. In contrast, from the perspective of system S prime, clock B prime is stationary. Clock A prime moves in the positive X prime direction at speed V prime sub A prime, and clock C prime moves in the negative X prime direction at the same speed as clock A prime. Again, offset clocks are avoided in the computation of clock A prime and C prime speeds in system S prime, and the use of Einstein's relativistic velocity addition formula is also avoided since it requires that time measurements be made with the use of offset clocks. Clocks A prime and C prime meet after clock A prime has traveled a distance dx prime sub 1, and then clock C prime proceeds in the negative X prime direction until it meets clock B prime, where they compare clock readings. The question we wish to ask is whether the difference in the time readings of clock C prime versus B prime will be the same or different for any given speed of system S prime.
So I'm just going to pause here for a second. So what I wanted to avoid is acceleration, because whenever an experiment that challenges special relativity involves any kind of angular acceleration or reversal in direction, whatever, everybody throws up their hands and says, well, that's not special relativity. Einstein only talked about inertial systems and special relativity, and you have a non-inertial system. So and they write off anything that's been shown. Here, what I'm doing is using completely inertial systems. And all I'm doing is transferring information between clocks, not changing the direction of any clock. I'm very careful to show that clock A prime happened to be wandering by clock B prime at a constant speed in the beginning. Clock C prime happened to be wandering toward clock B prime from the beginning. Clock A prime and C prime happened to pass by each other. And when they did, they exchanged information, and then clock C prime happened to wander over to clock B prime and exchange information at the end. There was no change in direction, no acceleration, no deceleration. So all of those objections to theories that involve, in the twin paradox, all of those objections about turning around, one twin has to turn around and come back, that's all BS. It's silliness. This experiment basically does the twin paradox experiment without any kind of turning around or acceleration. I did see someone comment about, does acceleration affect time dilation? I suspect that it does. I'm not good at general relativity. I haven't gotten there yet, but the thought is that gravity is similar to accelerating something, and gravity does change clock readings. So clocks tick faster in lower gravity and slower in higher gravity. I think that's been fairly well established experimentally. So I think the same phenomenon is going on. I just don't really fully understand how gravity pulls that off. I did see something about if you compute the escape velocity of something leaving the Earth, that it's the speed required to achieve escape velocity, and you plug that into the Lorentz transform, you get the amount of time dilation that gravity causes. But I don't know that. I'm just telling you something I saw. I don't know if it's correct or not. Okay, so far we've designed an experiment using all of Einstein's rules, inertial systems, no acceleration, no clock offset. I've said that word a lot, and I hope I haven't confused anybody, but we've never synchronized distant clocks. We've only synchronized adjacent clocks. So when you synchronize adjacent clocks, they do get identical readings. It's only when you synchronize adjacent clocks, because of the delay between the transmission of light from one clock to the other, that you come up with different readings. So here we've dispensed with clock offset, and we're only dealing with time dilation and the transmission of information between adjacent clocks.
So we need to solve for the readings on clocks A prime, B prime, C prime, and K. When clock offset is not used, the formula for time in system K is gamma sub V sub S prime times the round trip time elapsed on clock B prime. And since dx prime sub 1 is equal to negative dx prime sub 2, and v prime sub a prime is equal to negative v prime sub c prime, each leg of the trip is of equal duration in both systems K and S prime. And so dt sub K1 is equal to dt sub K2. In his 1905 relativity paper, Einstein gave us formulas that we can use for the time elapsed on clock K for each leg of the trip. We can solve for v sub a prime and v sub c prime using the following defined terms, keeping in mind that v prime sub a prime and v prime sub c prime are determined using a single clock to measure elapsed time in system S prime. And since dt sub k1 is equal to dt sub k2 and dx prime sub 1 is equal to negative dx prime sub 2, the amount by which v sub a prime exceeds v sub s prime in system K will be the same as the amount by which v sub c prime is less than v sub s prime in system K. In other words, speeds v sub a prime and v sub c prime are symmetric around speed v sub s prime in system K. Since no acceleration or deceleration takes place in our round-trip model, and since clocks A prime and B prime were synchronized to exactly the same time reading at the start of the experiment, and clocks A prime and C prime were synchronized to exactly the same time reading when they met, the difference in clock readings on clocks B prime and C prime when they eventually meet will be due solely to the difference in clock tempos, which according to special relativity are governed by the speeds of the clocks relative to system K. When we require clocks A prime and C prime to travel at the same speed relative to a single clock in system S prime, for example, relative to clock B prime, then dt sub k1 and dt sub k2 will be equal. We can then condense this formula to the following formula, where dv sub a prime and dv sub c prime represent the differential system K speeds of clocks A prime and C prime with respect to the speed of system S prime, which is also the speed of clock B prime. We find that the formula for the difference in clock B prime versus clock C prime readings is not independent of the speed of system S prime. Now let's study this formula for a minute. When clock C prime reaches clock B prime, it will report a different time than what is being displayed on clock B prime. In fact, clock B prime will always be slightly ahead of clock C prime, since the formula must yield a positive number unless V prime sub A prime and V prime sub C prime are both 0. This is the real answer to the twin paradox, which is not really a paradox once one understands that the symmetry assumed in special relativity is a deeply flawed concept. Acceleration and deceleration are completely unnecessary for one clock to have aged less than another clock. The effect is greatest when v prime sub a prime and v prime sub c prime are large compared to v sub s prime, and least when v prime sub a prime and v prime sub c prime are small compared to v sub s prime. Even when system S prime itself is stationary, such that V sub S prime is 0, clock C prime will display a reading that is behind clock B prime when they meet. In fact, the effect is greatest when V sub S prime is 0. So if the Earth is stationary in the universe and an outbound spaceship synchronizes clocks with an inbound spaceship while they are both in space, the clocks on the inbound spaceship will lag behind Earth clocks when the inbound spaceship returns. But if the Earth is moving rapidly through the universe and the speeds of the spaceships are slow relative to Earth's universal speed, then the clocks on the inbound spaceship will lag less than if the Earth were stationary in the universe. In other words, the difference between the readings on clocks B prime and C prime when they meet will vary depending on the speed of system S prime with respect to our reference system K. This difference in clock readings is a measurable endpoint within a single system. It's not some illusion subject to the biases of the relativity of simultaneity. This unexpected result has been attained by adherence to the rules of special relativity, simply by choosing to measure system S prime clock speeds with a single reference clock rather than distant offset clocks. I mean, obviously, observers in system S prime are free to use whatever tools are available to them in system S prime. To force the use of offset clocks instead of a single reference clock is like choosing to dress oneself in front of a funhouse mirror. I mean, this might help one to purposely gain or lose weight, but have no doubt that this would be a deceptive trick to distort reality. Why distort reality when we don't have to? Okay, what does this mean? Shockingly, it means that special relativity does not support the principle of relativity for all setups. It means that observers in system S prime will be able to determine an absolute speed for system S prime. It means that in order for relativity to make rational sense, the speed of any inertial system must be measured with respect to some universal preferred system of reference and not with respect to some arbitrary reference system K. And if one measures the speeds of clocks A prime and C prime relative to system S prime, one will be able to predict the speed of system S prime relative to that universal preferred inertial system. This has enormous implications for our universe. If time dilation, as described by Einstein, is real, it means that there is some universal reference system that grounds the laws of physics. The laws may be the same everywhere, but the measurements of the variables used in these laws must take into account the speed of the inertial system relative to the universal preferred system. And that has enormous implications for any physical constant that includes time as one of its dimensional components. Constants such as Planck's constant, electric permittivity, magnetic permeability, light speed, etc., to name a few, are constants that will most likely require recalibration with respect to the speed of the inertial system in which they're measured. All right, that's it for now. Please leave questions in the comments section, and please.
Okay, that was the video. So I'm open to questions, challenges, whatever.
So for the moment, I'll remove the video. Thank you very much, Joe. I think that was quite illuminating, and we have many, many comments and questions. And perhaps, with your permission, we'll go through them quickly, and then we'll get into a more detailed discussion with people in the green room. Something first, maybe just take the host's privilege of saying a couple of words, and you can tell me if you agree with what I've just said or if it's nonsense. It seems to me, to a certain extent, that your argument is a bit of a reductio ad absurdum. You've taken Einstein's SRT and the Lorentz transformations and indicated by your very detailed algebraic expressions where it will lead. In other words, it will lead to paradoxes that two clocks would show different time. Sorry, one clock would show a different time in the same frame, and also that contradicting the very basis of relativity, showing that SRT according to its own principles, would indicate a preferred frame. Now, you've done this in a very detailed way. Is that a fair comment, would you say?
I think it's a fair comment. I wouldn't call the end result a paradox. I would just say that it is it's the outcome you get when you dispense with the clock synchronization at a distance and just run time dilation with clocks that have been synchronized when they're adjacent to each other. So I wouldn't call it a paradox. I would say it refutes the principle of relativity as expressed in special relativity.
Okay, well, there are a number of comments, and mind you, some of them say a bit complicated, hard to find, it's hard to follow your analysis. But I mean, this indicates the depth that you've gone to in analyzing this, and it's very hard to explain this. But perhaps we'll bring up some of the comments, and it might be an opportunity to do that. Let me just see now. 2 o'clock. Quest is just saying that some etherists claim that the length contraction is caused by the push of the ether as objects travel through it. I think you mentioned in passing about this physicality explanation, perhaps, of length contraction, which you don't accept. That's fine. And actually, it's interesting. You mentioned earlier about your rejection of this, but your acceptance of time dilation. And we've discussed this a bit among ourselves, and certainly for my part, I accept exactly what you had said. That it's possible, and there seems to be indications that atomic clocks will vary in their rate. But we tend to, maybe most of us here, I think, not to use the word time dilation. We don't believe time dilates. We believe that the clock's slow, if you like, which is a different thing. Time itself is not changing. And you agree with that?
I agree with that, yes. In fact, I don't believe in time. I believe that whatever makes up our world is in different physical states, and that time is like a motion picture where you're looking at the frames, and you could take snapshots of where those objects are in the world in each frame, but that what we call the passage of time is just the movement of objects relative to each other in the world. I know I'm not making crystal clear, but anyway, I do agree with you 100%. I don't think time dilates. I don't think time is a dimension other than a human concept on this strip of film. It is the linear, it's as you scan down the film, that's what time is. But I don't think time is a property of the universe. I think it's just a human concept that we've invented to explain the relative motion of things as we perceive them. And
James Arrington has just expressed this, which quite possibly you agree with, but let us know. He said the Sagnac experiment, which you referred to briefly, is a way of showing that light at least travels with relative to the host inertial frame of reference.
Yes, I love that. The Sagnac experiment, I think, is brilliant. And I think it shows things that also refute special relativity. The Sagnac experiment was done in 1913. It was written off because it involved a rotating frame. But there were a couple of publications, I think in 2003, 2004, by Zhang et al. One of them was in Physical Review Letters, so it was well reviewed. And they essentially set up a closed loop system like in a Sagnac, but they moved a piece of it linearly. And they showed that the interference pattern was shifted as you would predict based on the distance that the detector was moved, and showing that you did not need rotation of the detector or the apparatus in order to achieve the Sagnac effect. And I actually have submitted a couple of papers, American Journal of Physics. They got roundly rejected because I didn't understand special relativity and all that. But I think that, the Sagnac effect proves that when you move a detector relative to, let's call it the universal preferred system, you actually get different speeds of light in both directions. The Sagnac effect, if you are in the moving frame in a Sagnac experiment, to you as that observer, light is going at different speeds in different directions. It may be going at the same speed relative to someone in the laboratory who's watching the Sagnac apparatus spin around, or Zhang's, what they call it, the clothesline apparatus move. Light may be going at the same speed in the frame of the universal preferred frame, but to an observer that's on the clothesline or on the wheel, light is going around the loop at different speeds.
Yeah, I mean, I quite early sort of concentrated on this, that when you push people in conversation, they do say what you say. Oh, either it's inadmissible because it's non-inertial, or other ideas. But it's very, very odd, and many of us, such as myself, who studied physics in detail in a third level, had never heard of the Sagnac experiment, nor of the Michelson-Gale experiment in the late 1920s. So it's most odd that textbooks don't even bring them in and then dismiss them. They say nothing about them. Very, very odd.
I see that Stephen Gift wrote that the linear Sagnac is by Wang in 2003 and 2004. Yes, Wang was another one of the authors. I don't know them personally, but yes.
Well, actually, very interesting, because Ru-Yong Wang contacted me about these conferences. We had a talk maybe a couple of months ago, and it came up again. And I was delighted. In fact, so delighted that I asked him, would he give a talk to us on one Saturday, but he sort of declined at the moment. I'm not quite sure if it was a language problem, or but he was quite happy to keep in touch with us and exchange ideas. So, yeah, I mean, Kev Con has just said that what he needs to use the Einstein addition of velocities equation. I think you did actually show that later on. The V1 plus V2 over 1 plus V1 V2 over C squared. I think that came out in one of your equations.
Yeah, so Einstein had a velocity addition formula. And I didn't realize this, but the velocity addition formula depends on the clocks being synchronized according to his convention. Otherwise, that formula doesn't work. So you need Einstein synchronized clocks for the velocity addition formula to work. And that's because the Einstein's velocity addition formula is just derived from the Lorentz transforms. It's the distance transform divided by the time transform. Right. And the time transform has the clock offset term in it. And so the velocity addition formula is also dependent on clock offset. If you take a clock offset away, then you can't use Einstein's velocity addition formula to compute combined velocities.
Right. Well, I'm going through this very briefly. Oh, I think there was one where it might have been Quest that I particularly want to ask Joe this. I'm not sure if he covered it yet. Yeah. Okay. There are other factors which we could, temperature effects and so on. We probably don't have time to go into those today, and we'd like to get to the green room people in a moment. I see one or two have logged in actually. So, okay. Yeah, well, Quest is sort of asking again in plain language. Would you say that? But we've already mentioned, the so-called anomalies. You say they're not paradoxes, which would come out of using Einstein's equation themselves. Because for my part, what I've done is I sort of don't even waste time going into these equations, because I believe that for experimental reasons, we've shown that applying the Lorentz transformations to ordinary mechanics or dynamics is incorrect. And then I've developed a theoretical basis to show that that's not so. But I think what you've done is very, very interesting. You've used the equations themselves, assuming length contraction, which you reject, and time dilation to reach these anomalous conclusions, let's say. So maybe we'll just go through this quickly. They were talking about acceleration and so on. And the equivalence principle and so on. Okay. Anything else that I think actually Rocham has agreed maybe with us. No need of the ambiguous terms, time dilation, etc.
I see a couple of interesting comments coming in from Stefan Gift, saying that the one-way speed of light can be measured and that the GPS system shows that you can measure it. So I just want you to think about something based on what I've presented here. If the time readings on GPS satellite clocks are influenced by their speed through the universal preferred frame, then their position relative to the solar system or relative to whatever that universal preferred frame is what will determine their tempo. And if, let's say, the Earth is moving, let's see, you're seeing it right to left, okay, and one of the GPS clocks is moving left to right, Earth clocks and GPS clocks will be reading differently. They'll be experiencing different tempos at that moment. As that GPS clock orbits the Earth, that will be reversed. And so I think the GPS clocks are actually, if you believe in clock, let's call it clock slowing instead of time dilation. If you believe that atomic clocks slow based on their speed through the universe, not their speed relative to the Earth. That's like small thinking. The big thinking is how fast are these clocks moving relative to the universe? Then there's going to be almost an oscillating effect between the rotating clocks and the Earth clocks, and they're going to be going in and out of synchronization. But we're not going to detect that because of the time delay between the satellite clock and the Earth clock. And so it's going to appear that light speed is constant between the satellite clock and the Earth clock, even though they are experiencing different amounts of clock slowing based on which direction they're moving with this, whatever we're moving with through the universe. I know that's complicated. I'll make another video on it, but I think you get the result that you can assume that light speed is constant between GPS satellites and Earth-based clocks, even though they're both undergoing different amounts of clock slowing at different times, depending upon which orientation they are in.
So a couple of our participants in the green room have sort of raised this question as well. James Keane has said he's actually measured the one-way speed of light and how it links in with his own theories of binary mechanics. And Dennis Allen has talked about Maronov's experiments. So I'll be bringing those two gentlemen up in a moment, perhaps to go further into this. Now, I was just about to ask, is anybody wanting to come up? And I think Roger Anderton has his hand up. So I'm going to add you to the stage, Roger. And what is your comment or question to Bill?
Okay, thank you. Very good. So you've been into this for 5 years. Some of us have been into this issue a lot longer, and
I feel your pain.
Yes, I think very much from the very beginning of when Einstein brought this out, people started disagreeing with it, and it's carried on and on and on. At a sort of like the present stage, it seems to be that from my direction, as many engineers say that Einstein's relativity is wrong. Because from our background, we have to work, we have to study engineering with a degree, and after we're free to actually look at what the physicists are saying about relativity. We look at it and say, oh, the physicists are talking a load of nonsense. But the physicist's response is to think, oh, engineers don't know what they're talking about, and they just ignore us. And that's been going on for ages. So I've been studying what's going on now for a long time. And when you start looking more into what's being said about special relativity, you end up with them saying different things. There are people who claim to believe in special relativity and believe it has a preferred frame. And there's other people who believe in special relativity say it doesn't have a preferred frame. Then there's other people who believe that Einstein made a mistake with his clocks in his 1905 paper. And there's other people who don't believe that. So the whole thing ends up with even the people who believe in special relativity don't have a unified point of view on the subject. Have you realized that?
Yeah, I get a lot of comments on my YouTube channel, which is called Ask Us Whatever, by the way, if you want to watch any of the other videos. And I get a lot of comments, and it's all over the board. People have different understandings of what special relativity means, from a religion to it's total nonsense and we should ignore it, and everything in between.
From my point of view, because the people who believe in it contradict themselves, that means it must be wrong. They don't have a unified belief in one theory. They've all got different beliefs about what that theory is, and that's what I've tried to emphasize quite a bit in some of my videos, that it's contradictory because it's people believing different things. And when
that can be, if I may say, good or bad. So in other words, in some instances, the fact that people are maybe analyzing it for themselves and maybe not coming to a particular dogma could be good. But we have discussed this, Roger, in particular in regard to the which was mooted today, the twin paradox and the paradox of non-reciprocity. They've introduced, I think, 57 different hypotheses have been introduced, probably to save the principle.
But the people who believe in special relativity, they've got the contradictory beliefs about it. They all believe their particular belief about relativity is correct, the correct one. So anybody who's saying different to what they're saying, they think that person's got it wrong. So you've got that. It's just chaos. So if you try to get into dialogue with these people, you're in utter confusion as to what particularly they believe about relativity. And so that just ends up with nonsense in the end, because they're just going to believe their version of relativity and not recognize that their version is not the same as necessarily as everybody else's version of it. So if you want, I don't know where you are. Are you in America?
In the San Diego at the moment.
Yeah,
yes.
I go to these places where they teach relativity, and I start arguing with the teachers of that subject. And so I'm in England, and in Oxford University, that they do a summer school often for adults teaching relativity. And so if you ever considered going to a sort of something like that, a summer school where they teach adults, you thought you could bring out your objections to the teachers or the professors and that, because you don't necessarily get the full picture just from reading textbooks. Have you ever considered that?
I hadn't considered that. No, I might need a bulletproof vest, but
yeah. But they give you the sort of the version that they believe at that time.
Yeah,
because relativity has undergone a lot of amendments, which they don't really admit to often.
Well, I think
what they're teaching is not always the same as what's in the textbooks.
Yeah. Well, it's almost like nobody goes back to Einstein's original paper. Very few people do. And I think they've learned relativity from textbooks and from their teachers. And then, a few generations have gone by and it's been handed down. But what I've done is I've gone back to Einstein's original papers, and I strictly adhere to what Einstein wrote in my analysis. And I think
but the papers, he writes his stuff in 1905, and he seems to change his mind in subsequent papers like 1907 and so forth. So he's sort of like changing his mind. And then it's sort of like, well, what is the final theory? You've just got all these changes of mind.
But as regards, analysis of the theory, questioning any of the ordinary sort of dogma, we have, and Joe, you probably experienced this today, we have a reasonably sympathetic audience today because most of the people here, have questioned it in some way or other, including myself.
Yeah.
But on the other hand, we do have a couple of people who are what might be described as more mainstream and think we probably are a bit mad questioning that. Unfortunately, I think maybe not many of them are here today, but I just alert you to that. So you might be having a easy ride of it. I don't know. So anything else, Roger, because we're running a bit short of time.
Well, one of the problems is with us dissidents is sort of like many of us say we look at Einstein and think he's wrong, and then we come up with our own theory. And so,
and we all disagree with each other.
If you've got 100 dissidents who agree Einstein is wrong, you then got 100 different theories.
Yeah.
And so
I think the important thing is to develop some experiments to test it. And it's challenging because, we're dealing with very fast light speed and large distances. I do have an experiment in my mind that might be interesting, and I'm going to try to design it. And it's something that you can do in a laboratory. We'll see. I think what really is going to count is someone comes up with an experiment to refute the theory.
Yeah, well, people have proposed things like that, and sort of like when we were NPA before we were CNPS, sort of like they were given an award out, SANAC award, and sort of like there's a large number of people who are thinking the SANAC experiment really just.
Well, it essentially did. It did. The Sagnac experiment showed that light travels at different speeds in different directions. And in this second rejection of this manuscript that I wrote, the reviewers had actually published on the Sagnac effect in the American Journal of Physics prior to me. And I stupidly criticized them in my paper. So they sent my paper to be reviewed by them. And they just, it's funny, they didn't understand. They could only work their equations in the way they understood special relativity. And to take it into, for example, they could not work with the Sagnac frame as the moving frame. They kept analyzing it as you're either standing in the laboratory or you're standing on this moving apparatus, but you are moving linearly, even though the apparatus is rotating. And it was just a bad analysis. And they just couldn't.
They have different distances, and that's the reason.
I think
the late Dr. Alf Kelly wrote to the CCIR, the international body of the ITU, I think, because they said, they're analyzed, they had papers, and they said the Sagnac effect is a relativistic effect. And he wrote to them and, questioned them and so on. And they sort of half-heartedly said, well, perhaps it isn't, but it's in line with special relativity. And we keep on hearing every day that the GPS system, which has the Sagnac correction for the rotation of the Earth, that disproves the constancy of the speed of light principle, but that it proves it. They say the GPS system actually shows special relativity to be correct. So they've twisted things around. So many of us would say.
So basically, many dissidents think that certain experiments, like the Sagnac experiment, disprove relativity. But then you get to the people who believe in relativity, and they say no, it doesn't. They don't. So it's the interpretation of the experiments a lot of the time.
Okay.
We've got.
So Roger, if we may leave it at that, please. Okay. Thank you very much for your contribution. And if there's anything further before we finish, please do.
I think that's a bit it. The issue is so much a complication of what people believe.
Roger has given us quite a number of talks on all these contradictions and different views of relativity and so on. So, by the way, just before we go, Franklin, who has said he said that the only way the second postulate could be so is if there's a preferred reference frame, is that the speed of light is constant. But I mean, the original postulate is, in my view anyway, humble view, quite correct. It says the speed of light is constant, independent of the speed of the source, which is true. But what they've done is they've generalized this because the source movement is equivalent to observer movement, and therefore they've said it's independent of the speed of the observer, which actually is a nonsense in my humble view.
Mm-hmm. Mm-hmm. And the Sagnac experiment shows that if the observer is moving, then you get different speeds relative to the moving observer.
Yeah,
and that's why you get a fringe shift.
And the reason you don't when the source is moving is that the source is giving rise to wave motion in a medium. It's exactly the same for sound. If you have a sound body which is moving in air, you still get the same speed of sound. But if the observer is moving, it changes. Exactly the same.
So let me throw out something very controversial, and I don't know if this is true, but in the alternative model for relativity that I've come up with, I do believe the source has an influence on light speed. And it's not a linear, it's not C plus V or C minus V. That was the Ritz model. Yeah, the Sagnac experiment shows that is wrong. The Ritz model doesn't work. Mine is a little bit different. It's actually the square root of 1 plus V squared over C squared times C. And how could light possibly go at different speeds through this medium, this field, whatever we want to call it, ether? Well, I think, when we think about water waves and we think about air waves, those are waves moving through massive materials, matter that has mass. And in order to create a wave, they have to move the mass. And so I think, I'm not an expert. Again, I'm not a physicist, but it's my understanding that as you change the temperature of the water, or the density, the material you're moving through, those waves will move at different speeds based on the mass of whatever they have to move to create the wave. I suspect that whatever this preferred frame is that electromagnetic radiation is moving through is massless. And therefore, I don't think it's constrained to a fixed speed, that the waves are not constrained to a fixed speed because they don't have to move a mass. So I think there can be a component to speed that's created by the emitter. But that's just a crazy idea I have right now. I'd never publish that right now. But it is something that I did an experiment in our studio where we passed light through a 2-meter glass tube. And we passed it down the 2-meter glass tube, and we looked at where the light impinged on a CMOS chip at the end of the path. And the light always hit, it was a focused laser light. The light always hit the same pixels on the chip 24 hours a day. And so then we took the glass tube away, and we weren't sophisticated enough to put it all in a vacuum, but there was air versus the glass rod as the pathway for light to travel, and it hit the same pixels all the time, 24 hours a day. I cannot understand how in a rotating, orbiting Earth, in a solar system that's moving, how can that light beam always hit the same target pixels if the source did not impart to that light some type of momentum in the direction of motion? I'd love to hear, alternative theories to that. But to me, the results of that experiment suggest that the source does have an influence on the direction of the light and therefore part of the velocity of the light.
Right. Just very, very briefly, I have looked at, how can we express this, that the original emanation of any radiation in a sort of an ether, let's say, retains a sort of a memory of that system. So in other words, when you're going, this would explain stellar aberration. If you're coming from another medium, another environment to an area around the Earth where you have a sort of an ether. Well, it retains the position and the angles that it originally were imparted to it. So that might be an alternative explanation. But I think we look forward to some further publication on that.
Okay.
Now, if I may say, there's a certain gentleman, I think his man, Frederick Lasai, if I pronounce his name correctly, that I haven't seen before. He's asked for the floor. Now, Frederick, you're muted and you don't have your camera on. Can you change that? Can you at least, you're unmuted now. I don't know if you have a camera. Well, I'll bring you up. What's your contribution, Frederick?
Can you hear me? Can you hear me?
It's very poor, very poor.
Yes.
Can you speak more loudly?
Oh, yes. Can you hear me?
Can you hear that, Joe? It's very.
Yeah, it's
garbled.
muted, but I can hear it. Yes.
Yeah. Okay. If you can speak loudly and slowly, because the quality isn't terribly good.
Okay. Thank you. Yes, thank you very much for this presentation. I find it very interesting because I've been working on this exact topic for more than 20 years. And some publication in different journals, okay. So it's all related to a whole method misunderstood or method chapter of relativity. So this is very interesting because for me it is a starting point for developing this new chapter, which explains on many things in physics. This is what I show in my last preprint article in my blog. You can find it in my blog. When you were talking in your presentation, Joe, when you were talking about the S-prime frame, you call it, sorry, the frame of the universe. So this is the starting point, which is already sometimes correctly stated in literature. Sometimes in literature, the twin paradox is correctly disserted. It's not
Frederick, I'm terribly sorry. I'm certainly not getting what you're saying. Now, unless Joe is getting it, I'm assuming that nobody else is really. So
what I got so far is he's asking about what I'm calling the frame S prime, but I don't hear anything beyond that.
Yeah.
Yes, the S prime frame.
I'm sorry about this. The quality is so bad that nobody is hearing what you're saying.
Yeah.
Please 10 seconds. I'll try to.
So maybe if you'd like to put a few comments in the private chat, or maybe just before we ask you to leave, I'm sorry about this. Just 5 words, very, very quickly and loudly, what you want to say. Just nobody is able to make out what you're saying, and the quality is too bad, and we're running out of time. So if you have a specific question on maybe what Joe is designating as the various frames, maybe you just.
It's a very important point. I am to actually demonstrating that in relativity there is a whole chapter in relativity which is completely missing, which has been completely missed during more than a century. Because
I'm sorry, Frederick. We just can't understand what you're saying. The quality is too bad. We're going to leave it. If you wouldn't mind just putting a comment in the chat, in the private chat, and we'll try to come back to it. But thank you very much, and I hope maybe we can get a superior line, maybe if you come back to us. So thank you for that. Now, because we have 1 or 2 other things. Actually, Vladimir has asked for the floor. He said briefly, and I hope he keeps to it because we're running out of time. But Vladimir, you're very welcome. So what points would you like to put to Joe?
Joe, thank you so much for very interesting talk.
Thank you.
I would like to, I'm not expert in special relativity, but I do like your conclusion. We must have preferred frame. Let me tell you, I'm a physicist. Let me remind you that physics is experimental science. And experimentally, it is already proved. We have such absolute frame of reference with microwave background radiation and with intergalactic plasma. And I would like to confirm you that there is a mass in this medium because its intergalactic mass it has about 4.8% of the whole matter of the world. That's why I talk about all this vacuum, no mass, nothing. It's absolutely wrong. That's why in my model, there is the medium, there is everything corrected by you right now. I'm so happy with your conclusion that even special relativity needs my medium. Thank you so much. This is the only one comment I want to leave. Thank you so much, Ian.
You're welcome.
Give
Thank
me
you, Vladimir.
this possibility to impress my attitude to this special relativity with absolute frame of reference. And I don't care about all the other possibilities. Let's come back to the real world, not to our beliefs. I hate this word beliefs. I hate it.
Right.
That's why please stop talking. We are physicists. We want to talk about experiments only. Religion, not religion. I believe this, I believe that. It's your opinion. I am not with opinion. I am with physics only. Thank you so much. And I'm so happy to be with you today. Bye now.
Thank you. So thank you. Vladimir actually has developed a theory which maybe is called WUM, World Universe Model. And he's actually given us a marathon 8 sessions on his subject because it's very, very huge. It's a big, huge tome over a number of weeks, over some months actually, over the summer. So those are available for viewing. They're obviously recorded on our so I'm delighted to have Vladimir's praise of your considerations there. There was one other point about the one-way speed of light. So maybe there were 2 points actually. Jim, you made a point about the one-way speed of light and that you'd done some work in this area.
First to Joe, this is a great presentation. You seem like an extremely bright man. I'm very glad you're here and presenting.
Thank you.
With regard to this experiment of the light hitting the pixels in your CCD camera, over 1 meter, is it possible where you didn't get a change? Is it possible that the size of the pixels is just too large compared to the distance of the source to the camera? And if a much larger distance, like many meters, heck, if it's laser light, you could go out, many, many meters, couldn't you?
Yes, it's a great question. The pixel density, I think, was 1 or 2 microns on this chip.
Oh, well, that's a huge size.
But over 2 meters, if the Earth is orbiting the sun at 30,000 meters per second, we should have seen about a 5 or 6 pixel shift in the pixels that were being stimulated by the laser light. If you just simply...
So you've done that calculation.
We did the calculation, yeah.
Okay.
And actually, that experiment was published back at around the year 2000. I forgot the name of the authors. It's on my website. But that was done under peer-reviewed publication. And again, they confirmed that whatever distance they were using was sufficient to detect the shift in the pixels. We saw absolutely nothing. And believe me, I was there staring at the screen, hoping that I'd see some kind of a shift, but I never saw a single shift.
And what do you conclude, sir, from that null result?
I conclude that the source is imparting the Earth's velocity to the light. It's changing the direction of the light. So when we are in the moving frame of the Earth, we are seeing no angular change in the light. But if you were somewhere stationary in space looking at our experiment, you would see a drift of the light. And the difference would be the aberration angle between the source and the target. So in stationary frame, you would see the aberration angle. In the frame of the laboratory, you don't see the aberration angle because you, the source, the target are all moving with the same velocity.
Okay.
And the light is moving with the same velocity, according to the way I interpret the experiment.
As a response to your interest in in designing new experiments which might shed light on some of these issues, I would like to mention that I've designed software at Binary Mechanics Lab. It's called the Binary Mechanics Lab Simulator. It's a free download, and which I've used to measure the unidirectional speed of light. Some other results are that the light speed is not constant, that it depends upon energy density of the vacuum. I've been able to derive, using this software, the actual measured approximate 300 million meters per second light speed from first principles without using any other unexplained measurements. I consider light speed to be an unexplained measurement, at least before my work in binary mechanics. So I guess my final point would be that perhaps you might want to look at, and I'm going to think about it also, as to what experiments could be done, perhaps using the Binary Mechanics Lab simulator software to further the goals that you're pursuing. Thank you.
Thank you.
Thank you very much. And Jim has done a lot of work on this binary mechanics, and a lot of this is available free to download on his website. May I just ask? Thank you very much, Jim. May I ask just briefly, by the way, Joe, what's the link to your website so people can maybe look at these things at their leisure?
It's called it's a horrible name. I wish I had a different name, but it's called askuswhatever.com. Just all one word.
Askuswhatever.com.
Yeah.
One word. Okay.
Yeah. And if you go to YouTube and type in Ask Us Whatever, you'll come to the video series.
Okay. Now, I wanted to bring just Dennis Allen up very briefly, because he made a point about Marinov's experiment, I think. Did you want to explain a little more about that, Dennis?
Yes. Here's a diagram of his couple mirror experiment. I don't know if you can read that or not. Because
it's a bit small, yeah. I can maybe put us down. And, yeah.
Marinov did another experiment called the chopped light experiment. Both of these had measured the one-way speed of light. And he also did some other, he has his own theory of physics. And he has a number of answers that all came out to be about the same. From galactic redshifts, 2.7 K background radiation anisotropy, Marinov's experiments, geostationary satellite signals, and muon flux anisotropy. And they all got the same answer, where they're measuring light in different, one-way light in different directions, and finding out which is the slowest direction, which direction gives the slowest speed, and which direction gives the fastest speed. And as I say, all these seem to agree pretty much. Of course, the error is larger, he said, but because it was done some time ago. And he refers to the universal reference frame as absolute space following Newton. But that's just a name, of course. And he finds, he calculates the speed of the laboratory relative to the absolute space, your universal reference frame. And he gets the direction, too. Mm-hmm. And the directions match up as well. Mm-hmm. And this is all explained in a book called Which Falls Apart, The Binding is Terrible. It's called Scientific Physics by J.P. Wesley.
What's the last name? Wesley?
Wesley, W-E-S-L-E-Y. James Paul Wesley.
Yeah, I've been doing a lot of work actually with Denny over the years on this. Denny has referred me to Wesley's work, and it's most interesting. he was an American. He ended up in Germany, actually. He's deceased now.
He was fired from every university he ever taught at. So,
Sorry, he was?
But fortunately, he was good. He was an artist, a good painter. I don't know watercolor or oils. I don't know. But he made a living. He had about 8 or 10 kids. And they moved to Germany, and he made his living. His day job was being an artist painting, and his night job was working on his physics. And he died in 2006, I think.
Okay.
This book is a 2002 book.
And the books are available from his widow, actually, in Germany.
Yeah, if you're interested, I can give you her address.
I'd love to get that, yeah.
Okay, well, just quickly.
Do you have contacts there if you want to send an email? Or if you have any problem, you want to talk to each other just through me, I have both your emails.
And the other is I receive emails at joe@askuswhatever.com. The same as my website.
Okay.
So I'll receive Joe, J-O-E, at askuswhatever.com.
Okay. So thank you very much, Danny.
You're welcome.
Yeah. So now, Stefan Gift, I apologize, Stefan. I think you've put a couple of questions in, and Joe actually referred to one of them, maybe briefly answer them, but at least you're here in the green room now. So I have pleasure in bringing you up. And if you'd like to put your points, Joe, it's Stefan to Joe.
Yes. Thank you very much, Ian, and good morning to everyone. And Joe, very, very interesting presentation. I followed you, and that method of critiquing special relativity has its advantages, but the issue of the interpretations, the relativists find very ingenious ways to counter your interpretation with their own, so I have actually abandoned that approach and sought another. But what I want to comment on, but excellent presentation. Let me see.
Thank you.
But my comment has to do with what you started out with. You said one-way speed of light can't be measured. Now, that used to be true, Joe. It used to be true when we did not have synchronized clocks, because synchronizing clocks, as you pointed out, required that you know the speed of light in order to synchronize the clocks to measure the speed of light, which you don't know. But the one thing that changed in the 1970s is the discovery of what is called the Earth-centered inertial frame, which the GPS uses, and it is known that the speed of light in that relative to that frame is constant. And as a result, they have been able to realize the GPS with synchronized clocks, both on Earth and synchronized with those moving in the satellites. So we have synchronized clocks, meaning clocks that tell the same time for the same event. So to measure the speed of light, you simply place one clock on Earth, let's say in New York, and another one in San Francisco, send a beam across, measure the speed, measure the time it takes, because you have synchronized clocks, and divide speed is distance over time. And as it turns out, it is easy to do that because there is an algorithm, if I refer to it as an algorithm or an equation, given by one of the specialists in GPS, which is Ashby, Neil Ashby. You must have heard of him.
Yes.
And he has a paper, a well-established paper. And in there's an equation that gives the time for light to travel from one point to another on the surface of the Earth. And I have used it to show that the speed of light changes in different directions, as you were suggesting. And it's in fact C plus V when you are going west, and C minus V when you are going east, where V is the speed of the surface of the Earth at the particular latitude. So I'd like to comment on that, because I think it's widely believed that you can't measure the one-way speed of light. And I actually think the GPS engineers know that we can, but they are hiding it from us because they know it gives the fact that the speed of light is not constant. I'd like to hear your comments. Thank you, Ian.
That makes a lot of sense to me. I did read some of Ashby's work, and there was a science paper, I think it was 1984, where they talked about a round the world experiment. And they talked about that if you Einstein synchronize clocks around the world, you would end up with a 200 nanosecond difference in calibration when you completed the circle. And it would be the opposite in the other direction. And I believe what they do with the UPS, what is it, UES? No, the Universal Coordination System.
Okay.
UTC, something like that. Yeah. I believe what they do, though, is don't they just make a mathematical adjustment to the clocks in order to maintain synchrony on the Earth? In other words, taking Einstein's convention out of the actual readings? This is where I would love to talk to an expert in GPS.
Yes, well, however they do it, they don't call it Einstein synchronization, because Einstein synchronization means you're assuming constant light speed.
Yeah. They reverse Einstein synchronization from the clocks based on the distance between the clocks.
But the point is, though, Joe, what does it matter how they have achieved that synchronization? What we do know is that all the whole GPS network is a network of synchronized clocks. However they have achieved it is a wonderful achievement, but that's what they have done. Yes. And that's what you need to measure the one-way speed of light. And we have it.
I agree.
And physicists don't seem to realize that for some reason. People just go around feeling, well, you can't measure the one-way speed of light, but it is easy to do it now that we have GPS clocks.
I just have not seen that published.
No, they haven't. I have published some papers on it, but the attitude of the GPS scientists is that they assume, here's how they say it, they assume light speed constancy in synchronizing their clocks, but they get the wrong result, so they have to make what they call a Sagnac correction. So they have to correct the wrong answer.
The Sagnac, and that's
removing. I said was called relativistic by them.
Yes, but they have to make a correction. Well, the fact that you have to make a correction means you've gotten the wrong answer.
Exactly.
And you know what, Joe? If you use the correct light speeds, C plus V if you're going west, or C minus V if you're going east, then you do not have to you can synchronize your clocks without making any correction whatsoever. Yeah. I suggest, Joe, the scientist that you should look at is Franco Selleri. He has done some work. Franco Selleri, I follow him closely, as Ian knows, and in fact, I believe Franco Selleri has the correct theory of space and time, which I have tested extensively and which I have been writing on for some years. Thank you, Ian.
Thank you very much, Stefan. And I might actually say, many thanks for that, as it happens, Stefan will be talking to us next time, in 2 weeks' time. He's given us a number of talks already on this work, and he'll be going further into this. So thank you very much.
Let me just add on Selleri. I've looked at some of his papers, but I think the original was Frank Tangerlini, who developed an alternative to the Lorentz transforms, where he got rid of the Sagnac term from the Lorentz transforms. It's what I call the clock offset term. And if you use the Tangerlini transformations in a Sagnac experiment, you get perfectly explain the results of the Sagnac experiment. So that's something, if you're interested, looking at that. TAN G H TANGHER LINI.
Okay, it might be interesting to have a look at that a little further, because it's interesting. And I'm so sorry that the time has caught up with us. Maybe that's a very good sign. It means that there's been so much information and there have been many questions. And I apologize. I know there are a couple of people here like Harry and Franklin and so on, who I haven't been able to bring them up. We don't have time. But and I'm sorry for cutting off Frederick as well. The audio was so bad and he didn't get the thing in. Actually, Harry is running these cosmological sessions on alternate Saturdays and also on Sundays. And I dare say out of school that we have a little bit post-mortem. So I think he'll have a brief discussion maybe tomorrow on the talk today. So we'll be able to do that. I'd like to hear what he has to say. But so what normally we do, Joe, is I'll give you maybe a minute or so just to summarize, if you wish, if you want to say anything more, you know, than you've said already, or maybe just summarize, or in view of the discussion questions we've had, and then it'll devolve upon me to close the meeting formally. So I'll give you the floor for a minute if you wish to say anything more.
Well, I've probably already said too much, so I won't say much more, but I think in essence, what I've shown is if you use Einstein's logic, coming from his 1905 and 1907 paper, and carry out the kind of experiment that the thought experiment that I proposed, you will see that it contradicts special relativity, and it requires a universal preferred frame for light signals to be transported through space. That's it. I'm delighted that you invited me to this, and you know, everybody keep up the good work. Maybe someday someone will publish some of our work in peer-reviewed journals, and let's just hammer away at it. There's a great book called the History of Scientific Revolutions, and in that book they talk about how the current class of scientists typically refuse to believe great new ideas. And it takes them passing away and a new generation of scientists coming up through the ranks to actually make paradigm changes in science. And I think maybe that's what we're facing.
Well, thank you very much, Joe, for coming here. It's our privilege to have had you. And I'm delighted that Harry, you know, made the introduction so that we had some emails going back and forth, and then we decided what to give. Your videos are very, very valuable, and I would sort of urge people to go back and have a look at the Ask Us Whatever site and so on. And we've had the opportunity of your detailed analysis. And as I said at the very beginning, I think it was in our private chat actually, that you're another person who hasn't been blinded by dogma. You know, you were not a specialist maybe in theoretical physics initially, and you were able to look at this with your analytical mind, having looked at other disciplines and so on. And we've had the benefit of that today. You've gone into very, very great detail. In fact, you've made things a bit complicated for some of our people. They said, "Could you explain it in simpler terms?" Well, I hope the discussion and questions and answers have aided a little, but you've given a very, very good exposition, and I'm quite convinced by many of the things you've done. As I say, I consider it a bit of a reductio ad absurdum system. You're starting by using the principles against themselves, you know, to show how they lead to inconsistencies. Yeah, so thank you very, very much for dealing with all these this subject in a very manly fashion, and dealing with all our questions and answers and so on. I'm very sorry if some of the points that were raised were not dealt with, but the website Ask Us Whatever gives a lot of information there, and of course I'm very happy to act as a conduit between anybody who wants to deal with any of these matters further and Joe. You know, as he said, it's Ask Us Whatever is also his website, but I'm happy to do that, and we hope now that we've you know made a sort of a permanent friendship with Joe, and he'll perhaps participate in some of our Saturday sessions, and indeed, if I may say so at such an early stage, come back at a later stage and give us you know further results from his work. So as the time has more than caught up with us, I must close the meeting. Thank you all for participating. Thank you for all your comments. Thank you for people in the green room. Thank you for your contributions. And of course, most of all, thank you, Joe, for having been such a good sport, for coming to us today. And we hope to see you again soon. So I'm going to end the stream now. And I'll wish everybody, wherever in the world he or she is, a very good day.